very good looking, and he's better looking than me. Sam's kind of shallow on this. So someone needs to hire Raul to be on the job market this year. So with that, he's here to talk about the data flow work we've been doing at MIT.
Thanks, Andy. All right, hi everybody, I'm Raul. This work is Meta-Dtaflows. It's a new distributed data flow model that we've designed for supporting the efficient execution of exploratory data flow jobs. So I'll start by motivating what an exploratory data flow job is, and I will do that with an oil field that you see on the slide, which contains a lot of different oil wells, each one of them with one of those mechanical devices that is essentially pumping oil from the ground. And so these mechanical devices, they want to pump that oil as efficiently as possible, but sometimes they have all sorts of problems, from mechanical problems, or there's a crack in the well, and for several different reasons, they may start underperforming. Now, one tricky thing here is that these oil fields are typically in remote locations. So if you want to gather data to even reason which ones are underperforming, what you do is you deploy some sensors, those produce some data, you put the data in some central place, and then now an analyst can say, well, how can I now figure out which wells are underperforming? So this analyst thinks hard about the question and maybe proposes a workflow such as this one over here, where we are going to first filter out some data, selecting those sensor readings that are more relevant, or perhaps some range of time in which we want to do the analysis. We will need to clean data because data is dirty, there will be miscalibrations and so on, and in the end we might want to fit a model that will tell us which of the wells are actually underperforming. So essentially will help us solve the question that we are after. Now, data is going to be large, so we are going to always be talking in this talk, I'm always talking about in the context of distributed systems. So because that data is large and we want to run this workflow, what we will do is we'll push that data into a cluster. We will pick the workflow and we'll express it into some data flow graph. And we want to do that because now we know that data flow graphs, the model behind Spark, Flink, and so on, is one good way of executing these data flows in the cluster with high performance and fault tolerance. All right, so far so good, but what I've told you so far is sort of the ideal situation. A very clean workflow with a one-to-one mapping to a data flow that's very simple. What happens in real life is that you looked into these workflows, and each of the different tasks that I've told you, they are going to have a lot of different parameters. And so filter data, you may choose to filter data one day, pick the last day's worth of data, apply some Gaussian mix for finding outliers, and apply a logistic regression to fit the model. That is one single option. And that is the data flow that you see here on the right. Another option would be to instead select 1 week's worth of data and use some support vector machine, for example, to do the classification. And when you start thinking about this, there's a lot of different parameters. It's just unclear which one is going to perform best. Which set of parameters is going to give us the best answer for figuring out which wells are underperforming. So the exploratory workflows are hard. Exploratory workflows is this idea where one single data flow is going to have multiple different parameters, and each parameter configuration is going to lead to a different data flow. As you see in the slide, the analyst needs to basically enumerate every single data flow for every single piece of different parameter configuration they want to try out, and they will to submit this to the cluster. They will need to wait until the data flows finish in the cluster, retrieve the results, evaluate the results with some script or something that they write, and pick which one is the best. Another one thing that I want to highlight here is that keep in mind that those data flows executing in the cluster are going to take a while. So these are not queries that run in seconds or sub-seconds. These are things that are going to take minutes or hours in some cases. So these are hard for two reasons. It's tedious and time-consuming for the human. That has to be basically checking these results one by one. But also when you think of this problem from the perspective of the cluster is really badly utilized because many of these data flows are basically doing the same kind of computation. They are generating the same kind of data. All right, so instead we propose Meta-Dataflows, which is the model that you see on the right. The idea here is that if you have an exploratory workflow and you want to sort of explore different bands of parameter configurations, we will pick the entire family of data flows that produces and represent it instead in a much more concise way, as you see here. And the key insight is that we can capture the user's exploration strategy. That is essentially the script that the user would need to write to evaluate the data flows. And we can pick that logic and insert it in the data flow by using two new operators, explore and choose, which you can see in green in the slide. And so the idea here is that Explore will open up or fan out to different parameter configurations that we want to try out. And Choose will have the user-defined function that is essentially going to be reading the results, applying the evaluation criteria, and selecting which one is good. This is the outline for the rest of the talk. I will tell you what are some advantages of Meta-Dataflows, of expressing exploratory workflows in this way. And I will also give you some technical details of what we did. All right. So the first opportunity of Meta-Dataflows, the first advantage is that data sharing becomes explicit. So now again, think of the exploratory data flow. There's this bunch of parameters that you want to explore, and one option that you have is you just enumerate many different data flows and you submit them to the cluster. Now chances are that those segments in the data flow that are common across all of the data flows are going to be generating exactly the same amount of data, the same type of data. So we are not sharing data, we are basically using the cluster in a very bad way. With Meta-Dataflows, it becomes now explicit that the data that can be shared will be shared. Now, this will have a link for some of you who have worked on multi-query optimization with result sharing. How do you share intermediate results to avoid computation? The cool thing here is that even though the idea is the same, the mechanism in which that we use to implement data sharing in Meta-Dataflows consists of essentially exploiting the relationship between the Explore and Choose. We know exactly which data can be shared. Another advantage is that data access patterns become explicit. So here for background, again, think of these data flows are running on a cluster. Each node has limited set of memory. If they run out of memory, they need to start spilling results to disk. So memory management is going to be a crucial thing that data flow systems must implement for high performance. So one thing that we observe with Meta-Dataflows is that many of the data sets that are created will be accessed repeatedly. And what that means is that along with the fact that we know exactly how we are going to be accessing the data, we should be able to design a memory management policy that performs better than, for example, least recently used, which would be the easiest one to implement. So we did that. In the paper, we present anticipatory memory management, which it's our response for this. And I won't get into the details of that one in this talk, because instead I want to focus on the last advantage of Meta-Dataflows. And the last advantage is that because now we have the user exploration goal in the data flow through the Explore and Choose, we are going to open up lots of possibilities for skipping computation. And I will get into the details of this with this example. So logical data flow, operator A, B, and C. A is cleaning some data. Let's assume that we fixed some operator. B is going to select a temporal window of data. And we have three options for doing so. We can select 1 day's worth of data, and that's going to be B3 at the top. We can select 1 week's worth of data, B2, or 1 month, B1. And then C is going to be fitting some model and producing some results. And the user's goal here is to find any of those parameters that leads to some model with a prediction error within some bounds. So assume just some threshold. Any of B3, B2, B1 that gives me prediction error below a threshold is good. What this means is that if, for example, we use B3 first, we get the results, we get the prediction error, and that is good enough, then there's no need to run B2 and B1 because we've already found one parameter that's good. Now, I want to dig in a little bit more here because I'm talking about this is possible because the user put this Explore and Choose. There are different ways in which this can be done. There's an exhaustive way of doing so. Like you can say, these are all my parameter configurations. I will enumerate them all, and I will put them between an Explore and Choose. That's what you see on the left-hand side. Alternatively, if the user has a little bit more of knowledge about the application that they are writing, in particular if they know that some of the parameters that they want to explore are independent from each other, then what they can do is they can split the Explore and Choose into different sections. And essentially here what I'm saying is that A2 and A1 can be explored independently from B3, B2, and B1. Essentially we are reducing the total number of parameter configurations that we need to run. But the bottom line is that regardless how this is expressed, we are always going to be able to find opportunities to skip computation if Choose selects one result that's good enough already. Now the tricky bit here is that I'm talking about skipping computation and removing nodes, but this requires to change the data flow on the fly. So we are going to need to modify data flow schedulers of current systems. This is true because if we want to support this Choose operator, we are going to need that dynamic control of the data flow. That is to say, we need to modify the data flow on the fly. So when you look at current data flow schedulers, they don't do that. If you see this example that I have here, if you want to execute D, we need to finish the execution of B and C first. Otherwise, D won't run. And that is at odds with our goal of executing B3 as soon as B3 is ready. Here, we want to execute B3 and give it to choose. We don't want to execute B3 and B2 and B1 and then give it to choose, otherwise we are in the same situation. So our response for that is branch-aware scheduling. For terminology purposes, I'm going to use a branch to refer to the subgraph in the data flow graph between an explore and a choose operator. So that's the highlighted part over there. And the idea behind this new scheduling algorithm is that we want to schedule individual branches first. And we want to do that because that way we can obtain results as soon as possible, give them to choose, so that choose can make a decision. For example, skip computation. The other advantage of scheduling individual branches alone is that all of the cluster resources that are assigned to this Meta-Dataflow are going to be available to one single branch. So keep in mind that even though I'm talking about one single branch, this branch has all the resources in the cluster available to it. If instead I would be running all of the branches at the same time, and these branches are going to run out of memory, then we are going to start spilling data to disk. So that's clearly, if we give all the resources to one branch, chances are that it will finish first. So once the results from choose are available, they are sent to the scheduler, who then might make a decision of modifying a data flow, as I explained before, schedule the new tasks that are necessary, and in particular, free memory as soon as possible. So if there's a branch that's been consuming memory and we don't need it anymore, we will drop all of the data sets that they maintain in memory, giving that memory to other branches that are more promising. All right. So there's a bunch of evaluation results in the paper. In particular, we have a breakdown of what are the benefits of each of the different advantages that I've explained today. But in this evaluation, I want to focus on one key question, which is, does Meta-Dataflows speed up exploratory workflows? In the end, this is sort of what motivated the entire work, and that's what I'll focus on that one. And to understand this, what we did was we set up experiments on a shared nothing cluster. We implemented Meta-Dataflows on top of SIP, which is a data flow system. And we are going to be comparing Meta-Dataflows against two different baselines. So there's going to be a sequential execution baseline in which, for all the parameter configurations, we will generate all of the data flows and submit each one of them one by one to the cluster. And then parallel execution, where it's sort of similar, but rather than submitting one by one, we submit a bunch of them at the same time. So this is a time series job where we are analyzing oil well data, such as the one on the motivated example at the beginning. The x-axis is going to represent the total number of branches, that is to say, the total number of parameter configurations that we want to try out. And as you see, the domain goes from 16 to over 1,000. When we run sequential mode, you see what you expect. The higher number of branches, the higher the running time. When we run parallel, and of that one, we run two different versions. We run the green bar is, we are submitting 4 parallel jobs at the same time. The red one, we are submitting 8. And in both cases, you see that it improves slightly over sequential, and this sort of suggests that when we were running sequential, we were not really fully utilizing the cluster. So that's why this performs a little bit better. The good news is, if we run Meta-Dataflows, it performs much, much faster. And it's actually very natural to understand why. Like, we have a choose operator that is now very quickly telling apart which branches are performing well, which ones are underperforming. So there's a lot of computation that we can skip. So we are simply just doing less computation. That's why we are faster. And this can be enabled because of that explore and choose in the model right now, rather than having a script outside. We also run a work for classifying images on top of a very well-known benchmark in the machine learning community. We use a deep learning job for that. So this job consists of 3 stages. There's a pre-processing stage, there's a training stage, and a validation stage. And we are going to look into 2 different options, an exhaustive exploration and an early choose. So just to remind you what those are, in exhaustive, we are going to put all of the different configurations, while in early choose, we are going to separate those that are independent. I know that pre-processing the data is independent from training the model, in this particular case, so that's what we are going to compare. The results show that when we do exhaustive, the only benefits that Meta-Dataflows have, as opposed to the parallel jobs, is some data sharing that occurs, some skipping computation. While early choose, you see how the performance of Meta-Dataflows is now much, much better. This is, again, because of all of the branches that we've pruned simply by noting that there are 2 parameters that are independent, but also because of all the computation that we can skip. All right, so Meta-Dataflows speed up exploratory workflows by sharing data, by skipping computation, and by performing better memory management. I we thought of this work as one step towards bringing some of the techniques that have been traditionally implemented in database management systems, things like multi-query optimization, things like dynamic re-optimization that you probably thought when I was talking about changing the data flow at runtime, on the fly. So we think of this as one way of bringing those techniques into the realm of data flow systems, which is sort of the state of the art to run jobs in distributed clusters these days. So I'll stop there. I'll thank you, and I'm happy to take questions.
Hi, all. Great presentation. Thank you.
Thank you.
I was wondering, you were looking at a sequential kind of analysis. What happens once you have cycles? So some of the analysis affects backwards. Will your model still be able to work with it?
Yeah, so in the paper we explain some sort of typical templates, things that people want to run. Iterative jobs is one of them. So if you have an iterative job, that is to say a cycle in the graph, what happens is that you can collocate the cycle within one branch, so that is between one explore and choose, and we can check what is the result quality after every single loop. So that is good, because if you have a different number of branches running in parallel, then you can quickly tell apart which one is probably not going to perform well. In particular, if you're thinking of methods such as hyperband, which is like how people have been thinking of basically skipping this computation on the deep learning side of things, it is possible to implement that in Meta-Dataflows by simply writing a user-defined function on the choose. So it's something that we support. It's better explained in the paper.
Okay, thank you.
Thank you.
Hi, thanks for the talk. It was really great. I was wondering, in your first experiment, what percentage of the model parameters would have been selected as good? Like, yeah. And then second, how do you choose which ones to explore first?
So what is the second question? How do I choose?
Right. So first, what percentage of the model hyperparameters would have been selected
So
as good?
here we are doing, right, so for your first question, we are doing a top one. So we are selecting exactly what is the best one.
So you end up executing them all?
No, because there's a, sorry, I said that completely wrong. There is a threshold. So any result that goes beyond the threshold is good.
Right. So what percentage of the possible models are?
Got it. I need to check the paper to answer that question.
Okay. And then how do you pick which ones to investigate first? Like, given your large number of options, how do you choose which model to evaluate first?
You mean at the end after selecting the data? Is that what you mean?
So initially you have these like 1,000 or so options to pick. You're looking for one that's above the threshold. How do you choose which one to investigate first? Like,
out of the ones that are above the threshold?
Out of the ones that you haven't started yet, you just entered the EX
Right.
node.
Got it.
You've got
Yes,
all these options.
got it. So that's a good question. So if we don't have any information, then we just pick random. The cool thing is that there's lots of functions that are either monotonic or convex. So if we know that they're monotonic, meaning that I'm looking for a threshold and I know that if I increase the threshold, I'm going to have fewer and fewer results that make it, then I can do a binary search. And again, this is something that's implemented as part of choose. For convex and monotonic functions, we have a table in the paper explaining what are the different options that can be implemented. Now I got your question.
Thank you.
Thank you.